Welcome to the deep dive. Today, we're heading into a really extreme part of our galaxy, Sagittarius C.
That's right. It's this star-forming region incredibly close to the Milky Way's center. We're talking, what, maybe 200 light years from the supermassive black hole?
Exactly. And understanding how stars actually form there, in such a wild place, it's fundamental, isn't it? For grasping the bigger picture of the universe, even, where the stuff of life comes from.
It is. But Sagittarius C, it's immediately got this puzzle baked in. It's absolutely packed with the raw ingredients for stars, gas and dust, super dense.
Uh-huh.
But it's just not making as many stars as you'd expect. Something seems to be, well, putting the brakes on star births.
Right, which is where these fantastic new studies come in. We're diving into two reports just out in the Astrophysical Journal, both using NASA's James Webb Space Telescope.
Webb, so we're getting a much clearer picture now.
We're an unprecedented look, really, inside this turbulent region. And these studies, they're pointing towards maybe a key reason why star formation is kind of stifled there.
Okay, so our mission for this deep dive, then, is to unpack what Webb's actually showing us about making stars in these extreme conditions.
Yeah, and we'll be focusing quite a bit on this intriguing idea about magnetic fields.
Yeah.
That they might be playing this really crucial, maybe unexpected role.
Sounds good. Let's get into it.
Okay, so this environment, 200 light years from a supermassive black hole. That sounds like a pretty intense place to try and build stars.
It absolutely is. You've got much stronger gravitational forces, way more radiation. It's nothing like the quiet neighborhood where our sun formed out in the spiral arms.
Right.
And Sagittarius C itself, as I said, incredibly dense, just crammed with all the gas and dust you need.
But seeing it clearly, that's always been the problem, hasn't it? All that dust in the way, like cosmic smog.
Exactly. The galactic center is, well, notoriously dusty, blocks out visible light like crazy. But Webb, with its near-infrared eyes, it's a game changer.
How so?
It basically sees right through that haze. We can finally observe details that were totally hidden before.
And the pictures Webb sent back are just incredible. There's this one NIRCam image. It covers like 50 light years across. Shows something like 500,000 stars, estimated, of course.
Yeah, it's stunning. And then you've got that huge splash of cyan color. That's ionized hydrogen gas.
What's ionized hydrogen again?
Basically hydrogen that's lost its electrons, so it's electrically charged, and it really responds to magnetic fields.
Okay. And the cyan stuff, it wraps around this really dark cloud, right? Blocking out everything behind it.
That's the one. Visually striking, but it also makes you think. Especially the size of that ionized region. It's about 25 light years across. That's surprisingly big.
And inside it, there are these weird, like, needle shapes.
Needle-like structures, yeah. And they're not all pointing the same way or anything. It makes you wonder, what forces are shaping things like that in such an energetic place?
It definitely gives you that aha moment, or maybe more like aha moment. It's way more complex than we could have imagined.
Okay.
So let's dig into that idea about magnetic fields maybe slowing down star formation. This is kind of the core idea in these new studies.
It really is. One of the researchers, John Bally, he put it nicely, said something like, for the first time, we're seeing directly that strong magnetic fields might be important in suppressing star formation, even down to small scales.
That feels like a pretty big statement.
It is a potentially significant shift.
So how does that work? How can magnetic fields act like, I don't know, cosmic brakes on making stars?
Well, think about how a star usually forms. Gravity pulls a dense cloud of gas and dust together, right? Tighter and tighter until it collapses, heats up, and bang, nuclear fusion starts.
Okay, the basic recipe.
But if the magnetic fields running through that cloud are strong enough, they can actually push back against gravity.
Ah, like a counterforce.
Exactly. They resist that gravitational collapse, so the material just can't clump together effectively to form a star, or at least it makes it much harder.
Okay, I think I get it.
Yeah.
You have all the ingredients ready to go, but they can't mix properly because these magnetic fields are, like, holding them apart, like trying to squish magnets together the wrong way.
That's not a bad analogy, actually. And, this isn't totally out of the blue. Radio telescopes on the ground, like ALMA and MeerKAT, they've given us hints before about strong magnetic fields in this area.
Right.
But Webb's infrared view, it adds this crucial layer. We're seeing the effects of those fields in a new light, literally.
And speaking of MeerKAT, didn't it provide a wider context view? showing those huge filament structures.
It did, yeah. A much bigger picture, like 1,000 light years across. You see these massive vertical filamentary things.
And it makes you wonder if the smaller needle-like things Webb sees inside Sagittarius C are kind of echoes of those bigger structures.
Precisely. It suggests the magnetic fields aren't just some local thing within Sagittarius C. They could be part of this much larger galactic scale network shaping the whole interstellar medium, the stuff between the stars.
Wow. Okay, now another really exciting thing from Webb was finding direct proof of powerful outflows coming from protostars, right? Stars that are still forming.
Yes, that's a huge confirmation. In the brightest cluster there, Webb nailed down that there are 2 massive protostars, each one already like 20 times the mass of our sun.
20 times, wow.
They're still going.
Still growing. Other telescopes hinted at them. Spitzer, Sophia, Herschel data helped too. But Webb really pinned them down and saw these bright jets blasting out from them, material being thrown off.
And it wasn't just the big guys, was it? They found signs of smaller stars forming too.
Correct. They compared the new Webb data with older ALA observations and managed to spot 5 likely candidates for low-mass protostars, still hidden deep in their dusty cocoons.
Those must be hard to find in such a crowded place.
Very hard. So finding even a few is a big deal for understanding the full range of star formation there.
And then there was this mention of shocked hydrogen gas, like lots of it. Yeah, something like 88 distinct features. That's where these jets, these outflows from the young stars, are slamming into the surrounding gas at high speed. It heats the hydrogen up and makes it glow in a specific way that Webb can see.
So each one is like a signpost saying, young star here, blasting stuff out.
Pretty much. And seeing so many so clearly tells us a lot about how stars interact with their environment right from birth in this extreme zone. And actually, analyzing that shocked hydrogen led to a cool bonus discovery.
Oh, what was that?
They found a whole new star-forming cloud separate from the main Sagittarius C one, and it has at least 2 protostars inside it, also firing off their own jets. They spotted it thanks to those shocked hydrogen signals.
That's amazing. Just stumbled upon another stellar nursery.
Kinda, yeah. Samuel Crowe, another researcher on this, he highlighted how important this is. Said something like, outflows were hinted at before, but this is the first time seeing them confirmed in infrared. And it's exciting because there's still so much we don't know about star formation, especially in the galactic center.
It really drives home how Webb is filling in these big gaps in our understanding.
Absolutely. And going back to those sort of thread-like filaments Webb saw in the hot hydrogen plasma.
Right, the cyan stuff again.
Yeah, the superheated charged gas around the main cloud. Those filaments look like another key piece connecting the magnetic fields to the suppressed star formation.
Okay, so what's the thinking there? How are the filaments connected?
Well, the idea is that these super strong magnetic fields, which probably get amplified by all the gas swirling around the nearby supermassive black hole, are actually shaping that hot plasma.
Containing it somehow.
Exactly. The intense gravity near the galactic center creates all this churning motion, right? That motion can stretch and strengthen existing magnetic fields. And these powerful fields then basically force the ionized gas, the plasma, into these long, thin filament shapes that Webb saw. Kind of like wind shaping clouds into streaks, but with magnetic force.
Okay, and the link back to star formation being slowed down is
that the same strong magnetic fields that are sculpting these big filaments in the hot gas might also be the ones acting inside the colder, denser clouds, resisting gravity, preventing collapse, stopping stars from forming easily.
Wow. So it's all tied together. The fields shape the big picture and interfere with the small-scale star birth.
Precisely. It seems like they're playing this dual role, organizing the hot gas on one hand and inhibiting star birth in the cold clouds on the other, a really complex interplay.
So looking ahead, it feels like these Webb observations are just scratching the surface, really, opening up new questions about star formation in these kinds of extreme places.
It truly is just the beginning. Samuel Crowe pointed this out, too, that the influence of strong magnetic fields, whether in our galactic center or others, on how stars live and die, the whole stellar ecology hasn't really been fully explored yet.
So this research really opens up new avenues.
Definitely. A whole new area for astrophysicists to investigate.
And it's also just a great example of how science builds, isn't it? Webb's findings, standing on the shoulders of work by MeerKAT, Spitzer, Sophia, Herschel. all these different instruments, giving different pieces of the puzzle.
Absolutely. It shows you need observations across the whole spectrum, from radio waves to infrared, to really piece together what's happening in these complex cosmic places. You get a much richer picture that way.
Okay, so let's wrap this up. To summarize our deep dive today, the James Webb Space Telescope has given us this just phenomenal new view of Sagittarius C, right near our galaxy's core.
And the big takeaway seems to be that powerful magnetic fields are playing a really significant role there, likely slowing down star formation by fighting against gravity in those dense gas clouds.
We've also seen Webb confirm these powerful outflows from young, massive stars' jets blasting out, and even discover a totally new, separate little star-forming cloud hiding nearby.
Yeah, incredible detail, and it leaves you, the listener, with something interesting to think about. These extreme conditions at our galaxy's center, these powerful magnetic fields, could they be typical of the centers of other galaxies, too?
Meaning star formation might work very differently in the hearts of other galaxies compared to their outskirts.
It could. It might fundamentally change how those galaxies evolve, how they look, in ways we maybe haven't fully appreciated. And it makes you wonder, what other forces, maybe things we haven't even thought of yet, could be shaping how and where stars are born across the universe?
A really fascinating thought to leave things on. This deep dive into Sagittarius C is definitely just the start. We can expect, I think, many more exciting discoveries from Webb and other telescopes as scientists keep probing these cosmic mysteries. Thanks for joining us.